Hello, and welcome to the Summer Series Programming Workshop. This one is called Steps for Intermediate Learners. I chose this title because I see a lot of content out there for beginner, like first robotics teams, like the real basics, and a lot of stuff on like Chief Delphi for like advanced kind of concepts, but the in-between's a little lacking. I know there's a lot of teams out there that started but don't really know where to go. So I'm Bryce. I was the lead programmer for Team 5199 in 2019. And then I'm presenting with Ashwin.
Hi, sorry, I'm Ashwin. I'm the lead programmer for 3476. I was the lead programmer in 2019 also.
So for the sake of this presentation that we're doing, the kind of assumptions that we're making, because we want to skip over some of the beginner stuff, is you know how to use like the driver station, and you can handle like getting to know a programming language on your own. Basically like all the provided software and like minimum expectations, like you have that down. And I know a lot of teams will find themselves with just one programmer, and that's all fine. But it's definitely a lot better of an outcome if you have more people working on the programming section, even if those people can be hard to come by. So I would say encourage everyone on your team to at least give programming a shot, even if they don't think they're capable of it. And they might surprise themselves. There's a lot of resources online to like get people started and get them going. And the other thing is when you have a team of programmers, like the big thing for doing teamwork in programming is you have to be organized, because otherwise you're not going to get anything done. Like all the work, any work you do will just get lost in files that are misnamed and stuff like that. And then in terms of development environment, just use VS Code would be my recommendation, the one that's provided to you by FRC, because it makes that organization step I talked about before pretty easy. I'd also recommend, if you're interested in this kind of presentation, checking out the Read the Docs page for FRC Programming Done Right, which I think is a really good resource, and An Idiot's Complete Guide to FRC, which covers more than programming, but has some good programming stuff in there. So starting the actual presentation, I guess, with what language you should use. There's actually a lot of options out there right now for programming languages, with the newest inclusion being Python, which I believe was officially supported starting in 2019 or maybe 2020, but it's there now, and it's pretty much just as supported as the other languages, so Java, Python, C++, LabVIEW, and each has its own benefits and drawbacks, but just use whichever one you think you'd be most comfortable with. They can all do the same thing at the end of the day, and I have some links for where you can get started with those languages for FRC if you so choose. What are those benefits and drawbacks? C++ is probably the fastest because it gives you a lot of access to low-level things, which means you can use memory more efficiently, and so it runs faster, sometimes marginally. Java is a lot more user-friendly, in my opinion, than C++, and still offers a little bit of that low-level access, but at the cost of it being a little slower. And then Python is not really a low-level language like at all, and it's sometimes pretty slow, but it's super easy to use, especially if you're just getting into programming, because the syntax is so like dumbed down and the whole white space thing. So one of the big parts of programming, in my opinion, in FRC, from my experience in season, was part of a programmer's job is just to sit in at the beginning, and when build season starts, they give you your challenge. When your mechanical design team's coming up with mechanical designs, you have to be able to let them know when they're making something that's going to be ridiculous to like actually make it work in software. That's a mistake that is made sometimes by rookie teams. I have a picture of a kind of a crazy example in the top right. They got triple jointed arm on a turret, etc. And that's because like programming for robotics in general, like just the field, comes down to the physics in whatever mechanical like mechanisms you want to use. You have to be able to break down the physics, how they work, and then get the sensors ready and the computer ready to control that mechanism. So that mechanism is like super complex. It's super complex to program.
Yeah, don't build crazy elevators on turrets is what he's trying to say. Yeah, so one of the things that's difficult sometimes is figuring out how do we prototype and iterate on our code, because before the season starts, you can start writing some code, and then as the season goes on, your program evolves. So that's what we want to talk about here. You should start with pseudocode. And pseudocode is not necessarily just comments. It can be function prototypes. It can be empty classes. It can be kind of the structure for what you think your program should look like as the season progresses. And then for a lot of things, it makes sense to basically draw out diagrams for what your code should do. And I put an example here. This is actually a diagram of how we were going to basically correct our turret's aim using vision. And you can see this is a reasonably complicated model, and it's often just very difficult to start programming in this math without having seen it drawn out and understanding what it's going to look like in the real world. So that's something you should do. And also you should be strategizing with your team. You should be talking through with your mechanical and your CAD people and figuring out what mechanisms are going to look like and what kind of stuff you're going to have, what points of control you're going to have and sensors you're going to have, because that's going to help you a lot. The other advice that we have for you is you really should be using those object-oriented features of C++ and Java. Those are very powerful features for being able to iterate, and you should be using them. And to that effect, you should be basically taking subsystems on your robot and really representing them as subsystems, as independent subsystems in your code. You should break those things up into classes, and you should implement the functionality that you think you might need as functions within those classes. And as you go on, you'll see that if you do that, it's really easy to start substituting methods and substituting things into those classes as you iterate. And we put an example down here. This is like a flywheel class. And let's say early on in the season, you write this prototype control method, right? And as you're doing that, if you're programming with good practice, for example, the thing that gets the RPM of the flywheel will be a separate function. And then later on in the season, when you go to write a more advanced control method, you already have all the building blocks that you need to do that because you wrote them for the prototype control method. And even more than that, when it comes to actually changing between those two methods or even switching between them, if you want to do that routinely, it's really easy because, again, everything is in your flywheel class, and maybe your flywheel class has this update method, and you just simply switch out which function you're calling.
Yeah, I would also say like it's difficult to break up a mechanism like into subsystems. Like it's difficult to break it up too much. Like you might think you're going too far, but you really can't.
Right.
Okay, so on to the toolkits that are provided by manufacturers and the APIs and libraries that are provided to you to make the robot work. This is something that sort of goes along with like basics. Like to get the thing working, if you have Talon SRXs on your robot, like you have to use the toolkit to install certain things. And you might already know how to do that. But the other thing that is worth noting is with those devices, there comes in the API a lot of built-in functions for you that maybe have been overlooked before by some people. There's a CTRE toolkit, and there's an API that goes with that for your Talons, the new Falcon 500, and even just for sim motors. And you can feed data into from an encoder or something into that controller, and it'll automatically do things like motion profiling or like velocity control and things like that. It'll do that for you. Definitely get familiar if you're just getting into programming in FRC with the library that's provided to you by the first partner university, WPI, Worcester Polytechnic. There's all the different like basic functions you might need in there, so you don't have to necessarily do those yourself, or maybe example code that you might need to get going. That's all in there. And also look at the different robot bases that are available and think about which one might work best for your robot. Some of the hardware even will, like I said, require you to have certain toolkits to install, like the CAN bus, like device ID manager on the Rio. Like you have to do that for CTRE devices and stuff like that. Here's a picture of the Phoenix tuner where you do that device ID handling, and you update firmware and things like that. And that's just something you need to get things working. It's pretty easy to use. It's like pretty intuitive, and they have all the information you need to get it working in the documentation for it, which I have linked in this PowerPoint. And then here's a picture of the API, the library basically of functions and enumerated types that comes with the Spark Max motor controller. And you can see that there is, you can read from the Neo motors. They come with an encoder, and they have a function already to read the encoder output. So that's maybe, if that encoder suits your needs, that's a step you can skip. There's things like that you can do pretty easily because it's already there. And now we're moving on to the next section, which is about how you give your robot a view of the field and like the outside world, I guess, with sensors. So sensors and single board computers are, all the different things at your disposal for giving the robot some kind of eyes and ears. So the rangefinder that comes in the kit of parts, any cameras, color sensors, gyros, encoders, and all of that gives you data about where your robot is, what it's doing. And then single board computers like a Raspberry Pi, or maybe something faster like an NVIDIA Jetson, can give your Rio, because it's not the fastest computer in the world, access to more ports for more sensors and more computing power for doing more complex things. So here's some common single board computers. There's a lot of vision tracking that happens in FRC now. And this is something we're kind of going to gloss over in this presentation because there's already so much out there. But these are good examples of ways single board computers that interface with the Rio come in handy. So the Limelight, which you can buy and just plug into your Rio, and it'll give vision tracking working, or you can get your own Pi camera and your own Raspberry Pi and use Chameleon Vision to get the same thing done, vision tracking. And it's not as difficult to set up as you might think, I guess, I would say. And there's markers all over the field that make it relatively intuitive. The data that you need from these devices, you can pick up over the network on your robot, which is like the Ethernet cables that run around. And it's done with network tables for these two particular devices. There's also, of course, encoders. And encoders are a fairly simple thing. It just counts how many times a shaft has rotated. So there's a couple ways that encoders will do that. There's Hall effect or optical encoders, are probably the two most common. And it allows you to do two main things, which is move a mechanism. So let's say an arm to a specific position, because you know where the shafts of the motors have rotated, so you can see where the arm is going, and you can also see the rate of rotation of the motor. This is oftentimes, actions like these are handled with the PID controller internally in the motor controller, which, like I explained before with the API, you get access to through that API, and it's fairly simple. And we can also use this data in programming when making our own autonomous code, so just driving along paths, or maybe controlling an arm using the encoder data, like I said. And then there's IMUs and gyros. They tend to mean the same thing. An IMU is just a sensor that can give you, with varying degrees of accuracy, the orientation of your robot in any of the three like cardinal directions, or any of the four cardinal directions, excuse me. It's like north, east, southwest, or its angular velocity again can be measured with this, and like where it's facing at the moment can be useful for the case of autonomous driving, because you can check if you're facing in the right direction before you do anything. There's this thing that happens called drift with the gyroscopes in these devices, and that's something you will have to learn to account for as well. But the sensors that are offered in an IMU package, like the Navex MXP, for example, is a common one. It interfaces with the RoboRio pretty easily. Comes really in handy for doing all kinds of things with the robot, including autonomous driving with an operator, like a driver, or many other things. And I also wanted to talk about human interface devices. This was something that came up for my team big in the 2019 season. It's really easy now to get an Arduino code-based device like a Teensy LC, which I have pictured in the bottom, and just hook up a bunch of arcade buttons off of Amazon to it and stick them in a panel and give them labels. And all of a sudden you have direct inputs from the operator or driver saying that they want to do something, instead of having some kind of like shortcut workaround for press the left trigger and the A button at the same time to do this. You have more buttons available to you that make it more intuitive to operate the robot. And this can help a lot actually playing the game. And it's not a particularly difficult thing to learn to program if you already know object-oriented programming, because Arduino is extremely accessible. So I think that this is something that a lot of teams should consider adding to their repertoire of like things you can program to make the robot better. And another thing to consider is providing the driver and the operator with some kind of visual feedback when an action is taken, whether that be like a light or a number changing on the smart dashboard, which is something you can control in code, of course, or having a camera somewhere on the robot that gives you vision of whatever side of the robot, and having that displayed on the computer at the drive station. Ashwin told me about a team with an interesting workaround for elevator positioning, where they had a camera positioned facing a measuring tape that was strapped to the elevator, and instead of actually using an encoder to read its height, they just looked at the measuring tape through the camera, which, you know, that's something you can do, I guess. So now moving on to controlling your robot well.
Yeah. So, you know, control is one of those things that both in autonomous and on top of your driver control as an augmented thing in driver control can really take your game kind of to that next level and really give you a competitive edge. And it's something that a lot of teams don't do, but really could implement fairly easily. So we want to talk about that a bit. The two simplest types of controllers that are commonly used in FRC are the bang bang and proportional controller. So starting with the bang bang, it's a two-step or on-off controller, and you'll commonly see it called hysteresis. And it's a feedback controller that basically switches between an on and an off state. It's exactly what it sounds like. It goes bang, bang. So the advantage is it's really easy to implement because there's no gains or no constants to tune, and it's very, very effective for certain simple systems. And on average, you'll see that if you use a bang bang controller over long periods, the average state of the system is going to be your desired set point. But the disadvantage is that you will see oscillation around the set point, and on certain mechanisms like elevators and arms, it's going to lead to very jerky kind of movement. We would probably recommend using it in something like a flywheel, where you will not really see that oscillation and it won't lead to jerky movement. And this graph here on the right kind of shows you what this controller does, but the idea is that beyond a certain set point, you don't apply any control, you don't apply any signal. So what this is showing is like controlling temperature with a heater and a bang bang controller, and you can see that when the temperature is below the set point, the heater is on, and then as soon as it passes that threshold, you turn off the heater, which is great, and then the temperature starts dropping, and then it turns back on again. And on average, the temperature is going to stay at that set point, but you can see that it oscillates. And for something like temperature or flywheel RPM, this might not be a problem, and it's a great controller. Now, if that doesn't work for you, proportional control is also pretty simple. And instead of just turning on and off, it actually applies input which is proportional to the error measured by the sensor. An error is usually defined as the set point minus the actual value of the sensor. And what this does, the behavior you'll see, is it enables basically a throttle down in sense as you approach your set point. So the advantage is it's very effective, and it's a lot more smooth than Bang Bang. And it can even account for certain kinds of noise, like being bumped by another robot in the field, or more friction than you might expect, or something like that. It can be tricky to tune the constant. There's a constant that's involved. It's basically the proportionality constant. It's how much signal to apply proportional to your error. And it's subject to undershooting because of what's called steady state error, which we will talk about a little later. But it is appropriate in a lot more applications. You will see this used in drivetrains, in flywheels and elevators and all kinds of things. And this graph here basically shows a proportional controller with three different constants for the proportional controller. And that blue line is the set point. And you can see that the system with a high proportionality constant basically gets up there to the set point, but then overshoots and then oscillates around it. And with a low constant, it doesn't quite get to the set point, but it almost makes it there, and it kind of throttles down smoothly. But there is some steady state error, which we'll talk about. And here's the code for those, and you know, you notice that these are really simple. These are both 2 lines. And it really is this easy. You might have to limit the output range or whatever, but otherwise you should be able to just kind of plop these in there. The only thing that might be tricky is tuning KP, and that's just going to take some trial and error. There are certain methods to doing it, which we're not going to cover here, but you can look those up if trial and error is not working for you. So sometimes the proportional controller alone is not sufficient, and it does have some problems, which we talked about. We talked about how it can overshoot. There can be oscillation. There can be steady state error. And because of that, it basically leads to this PID controller, which stands for proportional integral derivative. And these are kind of fancy terms, but in truth, they're very simple ideas, and we're going to just break it down and talk about those ideas. So derivative is basically a calculus term for instantaneous rate of change. But because our controller is running so fast, the average rate of change between iterations of the loop is a pretty good approximation. And basically what we do is we can limit the oscillation of a proportional controller by scaling the output signal by the rate of change of the error. And that's, again, given by error minus previous error divided by delta time, which is the average rate of change of the error. But because we're running so fast, it serves as a good approximation of the instantaneous rate of change. And then, again, we're going to multiply that by a gain constant for the derivative term. And if you start thinking about what that actually does, you'll basically, you can imagine situations where if the error is decreasing very quickly, the signal will be dampened. And the opposite way around is true too. If the error is not closing in quickly, then the signal will be larger. So I keep talking about steady state error, and I should probably explain that. Steady state error is the idea that there are some errors that act continuously on a system. That's things like gravity and friction. And the idea is we just want to get rid of those. We don't want to have our proportional controller deal with that kind of thing. And it's also the case in systems with high inertia, like flywheels. So what we do is we use this integral controller as part of our PID. And the integral is this idea of the area under a curve. And basically, again, since we're iterating so fast, the area under our error curve against time, it can be approximated pretty well by rectangles. And what we do is we use the integral term scaled by a constant to prevent steady state error. As far as tuning goes, what we recommend is basically raising the P gain until you're oscillating around the target, raising the D gain until you've dampened the oscillation, and then adding an I until you've eliminated your steady state error. So this is some code for basically a full PID controller. And again, it's very short and it's reasonably simple. You can see what we're doing is we're getting the delta time. We call this controller continuously, right? And we're basically, the accum variable is the integral term I'm talking about. At every iteration, we're adding in the error times delta time. And then the output signal is really just going to be the Kp times the error, just like the P controller. And then Ki, which is the integral constant, times the accumulated error. And then Kd times the rate of change of the error, which is the error minus the previous error times the delta time. And then that's really all there is to it. And what you'll find is that this controller is really, really effective for a lot of things, and it gets used very often in FRC. And like we mentioned earlier, this controller is so common that it's built into things like the Talon SRX and the Spark Max. So you should be able to get this going pretty easily.
Yeah.
So a lot of newer teams also find themselves struggling with how do we do the autonomous period? How do we basically move the robot without a driver? And it seems like an extremely difficult thing, but in truth, it's not that complicated once you understand these controllers that we were just talking about. I will note, driving 2D pads is kind of a complicated subject, and really you can go infinitely in depth into that, and you can look at controllers like Pure Pursuit or try trajectory falling, but I would recommend first getting like a one-dimensional case working, the kind of thing where I can tell my robot, move 20 inches forward, and it moves 20 inches forward. So at a minimum, what you really should try to do in autonomous is have functions that make it really easy to drive pads made of discrete linear segments and turning in place. So I've kind of given just a little bit of structure for what that code might look like here. You can have like a move function where you put in a parameter in inches, and then it basically converts that to encoder ticks, and then does a PID or a P controller on that encoder, and then it moves you to that location. And then in your autonomous, you can imagine chaining together these move calls to do things, and it's going to look a lot cleaner than just using time. And even if you have to use timing, like delays, like starting motors and then delaying and then stopping motors, you can still use functions. You can basically determine a constant like inches per second, and in your move function, you can use that constant and make things cleaner. And you can do the exact same thing for turning. Instead of PIDing on encoders, you can use your gyroscope, or you can use time again. And then on the right, what I included here was like actually having sort of a pathing library, because once you have those functions, it's pretty easy to write something where you can just put in points on the field that represent actual field coordinates, and then drive to those points, again, with those discrete linear segments and turning in place. So like what this one does is it basically iterates over all your points, and it computes, if you can imagine, if we're on some arbitrary point on this path up here, it computes basically the vector from the previous point, and then it tells you how much to turn, and then you turn that amount, and then you move. And actually, there's an error here. It should be the next point minus the current point, but it's the same idea. So this is like an example of a more complicated controller. This is for driving 2D pads. It's a Pure Pursuit controller, and it's kind of beyond the scope to talk about, beyond the scope of our presentation to talk about how to actually implement this. But the basic idea is that There's a look ahead radius, which you can see illustrated by the circle. And you can take those pads that you made, and instead of just driving those lines and turning at the endpoints, you can basically track the path, and you can follow an arc, a smooth arc, to drag the path. Another thing you might see mentioned a lot is motion profiling. And this is just the idea that we can use PID to execute smooth motion and control the velocity of our system. Instead of using PID for position, like we talked about previously, we're going to use velocity, and we're going to use our knowledge of 2D kinematics. And if we do that, we can not only control our velocity, but we can also make sure we end up in the right position afterward. The basic idea is you can write a function where you specify the max velocity, the max acceleration, and the desired position. And then, as a function of time, I can compute a target velocity at any given point. And you can kind of go through and derive this yourself. There's also lots of code out there, and I provided one example here too. But if you kind of go to your basic kinematics from physics, it should be pretty easy to follow like a trapezoid motion profile. One of the things that we really recommend you do is use version control. Version control, we recommend Git. It basically is software that lets you keep track of all your changes to your code, and also makes it really easy for lots of programmers to develop the same code, basically different parts of the same program, and then on what are called branches, and then they can merge them together to make one final program. GitHub is commonly used too. Don't get it confused with Git. It's actually a different thing. It's a place where you store Git projects, and these projects are called repositories. And it does have some very useful programming features like issue tracking, which should make it really easy to collaborate. Different versions of the same files are stored as commits, which basically contain the changes to your tracked files. And to actually use Git, again, there's a lot of literature out there, but you can access it through your command line, and it's a really good thing to do it that way, but also there is a desktop client, which makes it a little easier to use.
Yeah, one of the things that you and I have both seen some of the more rookie teams like lacking in terms of collaborating with code is using Git. I've seen teams at competitions who, instead of having like a GitHub profile where they keep all their Git projects, they have like a thumb drive or like a laptop that has everything on it. And I've seen teams lose all of their code at a competition. Like it's gone. Whether the guy's not there, they don't have the flash drive, the robot breaks down, they have to change it, it's gone. And I've had to I remember one competition, I had to rewrite all of the basic code for an entire robot in like 5 minutes. And all you really get it to do was like drive. Like there was no point in even trying really. And so version control is really important just to have backups if nothing else, but also for collaborating for sure.
Yeah, it's a very powerful kind of feature too, because it lets you do stuff like as you're writing code, if you realize that you overwrote something or you made a mistake, you can just go back. You can go back to any version at any point in time. So it's very useful.
For sure. Another part of sharing code with other people and your teammates is making sure you can all understand in your, the GitHub folder you create, so the project you're creating, you gotta all kind of understand the logic behind what you name folders, how like mechanisms are broken down, class names and variable names, so that it doesn't, for one, just so it like is more organized, like it looks neater, but also just so things don't get lost. A good example is, of course, separating your robot by mechanism, like we talked before about. You can't really split up the robot too much, but definitely discuss with the people who are collaborating with you, the mechanism that controls driving is just the drive train. Like it's not this other folder that is also called drive. That they should either be together. You should all understand how it works. And then a common practice is using a standard like camel case for casing for naming variables, so that when you're just trying to type out code, and you're trying to recall a variable from a class someone else created, and you type it out. Because it's not in camel case, you're like, what is it called? I have no idea. And you have to go look. It takes up time, which is kind of annoying.
Please don't name your variables things like good and bad. We did have that in our code. It was very confusing.
Having good file and variable like naming conventions and practicing them, like don't just come up with these and then not do them, like practice them, practice using them. That'll help you get organized a lot, and it makes not only like your job easier, but it makes the people who come after you and want to look at the previous season's code, it makes their job easier too. And another thing is comments. I'm guilty, like everyone else who has ever programmed anything, of making code with no comments in it. And it's not a good practice. Like, I'm not proud of that, really. You should always comment your code, especially for these group kind of projects, so that other people can understand it. And also just to make your job easier, again, so that you can debug it more easily. Like, you might write a piece of code a week ago, you come back to it, how does this work kind of thing? You have to sort of go through the whole thing again. Comments really help.
Yeah, and then the last thing we kind of want to cover is just how do you maintain your old code and code that you're going to keep using? Because this is something you should be doing. I mean, you absolutely should do this, because you're going to find that as you go through more seasons, you solved problems that you're going to encounter in future seasons. And it will help you both avoid wasting time writing the same thing and also repeating your past mistakes. So again, that's where GitHub comes in. You really should be using version control in Git, and you should be backing that stuff up. And if you've been making good use of object-oriented programming the whole time, what you'll find is that it's really easy to recycle old classes and methods. I mean, to the point where I can tell you on Code Orange what we do is we have certain classes. We have things like our Pure Pursuit controller, or we have a class called Orange Utility, and we build those things out season by season. And every year we literally drag and drop those Java files into our new program, just exactly how they were. So you should be writing your code with that kind of reusability in mind. And the example that I gave here, which I think is a very common example, is if you find yourself finding the magnitude of a vector over and over again, you should have a get magnitude function. And you can put that anywhere you need to find the magnitude of a function, and you can put that in your utils class as a global function or a static function. But even better design would be to actually write a vector class, and it has properties like x and y and get magnitude and add and cross and dot, and whatever you need in your vector class. And you'll find that as you solve more problems, you'll start building out this class, and eventually you'll get to the point where when you solve a similar problem, you have all the infrastructure you need to solve it.
I've even found between like myself and alumni, like if we build out classes that we reuse a lot, and unrelated projects to FRC, you can go grab that class or piece of code or call back to that knowledge and use it somewhere else, like completely. And that's really the power of object-oriented programming. And so definitely take advantage of it.
Right.
So that's the end of our presentation. Those are links above to the GitHub repositories of our teams. And if there's any questions, we'll take them now. Do you have the YouTube page open?
I do. I have it open. I don't see anything, but we can wait a bit, see if anyone has any questions.
Thank you.
Okay, so Rick is asking, how do you typically get new members to join programming? Okay, so let's see. You might have an answer to that too. What I will say on that is that is difficult, especially because programming is one of those things where you do need to know like the basic stuff, like the syntax of the language, conditionals and control statements and stuff before you can start working on robot code. But what we do on Code Orange is, one is we have off-season training. We have people who know programming, who are basically holding workshops and teaching other people on the team, and just getting them comfortable with basic stuff. And that way, when the season starts, they can start programming.
Yeah, I would definitely say the same thing. Like it doesn't take that long to pick up enough knowledge to like start programming a robot, but like the sooner the better. So if you're trying to recruit more people, either like this goes with recruiting new members, like go out of your way to find younger people in, let's say, your high school and get them going with just making like a simple robot with a Raspberry Pi and like Python or something, or just learning code like on the computer, like Java code, whatever your team standard is. Like just get people using it, and they'll find if they're really into it, like they're hungry to tackle more complex problems. And if you're talking about more like getting people to learn it, that's its own sort of topic, and there's tons of information online if that's something that you're lacking in, for like getting started with that stuff.
Yeah. Paul is asking, was the derivative term supposed to say divided by in your PID sample code? Yes, that was an error. I just saw that. Thanks for pointing that out. So on slide 22, where we give the PID sample code, we show KD times or minus previous error multiplied by DT, but it really should be divided by DT because, again, we're finding the rate of change there. So yeah, thanks for pointing that out.
Yeah. Tina asks, what is the best way to learn a new language? In this case, Python. So I can comment on this because Python is like, at this point, it's one of the only languages that I use to do like a lot of things. It's really powerful. I love Python. It's easy to pick up if you really just get started. Like the advantage of Python is, it's kind of slow, but the advantage is you can just like make code easily on your desktop. So like a good resource, I would say, if you're looking for a book or some kind of website, is there's pythonprogramming.net for Python, and there's a book called Automating the Boring Stuff with Python, and that's like how to do PC automation kind of stuff. So like, just little scripts to like do things automatically on your computer, and that's sort of how I started.
Yeah, I will say books are really, really good, and they're often very underrated. The cool thing about books is that if you go to the library and you pick up a book, it had to get published, which means that there is a standard that book had to meet for it to get published, which is not true of everything that you find on the internet or on YouTube. So yeah, I would really recommend books. They're often very good.
So Tina, I would definitely, if you're into Python, just start doing something, get a book, and just use all the online resources available to you, especially if you're talking about FRC. It's now an officially supported language, so it'd be a great step for doing FRC programming.
Paul is asking if we wanted to start using Python programming on robots, is there a less expensive option, the RoboRio? Yeah, there absolutely is. The tricky thing, so the RoboRio has WPI lib, which has a lot of nice functions in it for robot programming. You might not be able to use that if you don't use a RoboRio, but there are other microcontrollers out there and microprocessors that work really well. I think I would definitely recommend looking into like the Raspberry Pi. That's a very common one for really simple things where you don't need like a full Linux operating system. You can use an Arduino. You can also look into the NVIDIA Jetson Nano, which is a much more powerful microcontroller, but it's basically able to do a lot of cool things with artificial intelligence and with image processing. So it's a good controller.
I'd say the cool thing as well with any of those is like articulating that to FRC later. Right. You can reuse those microcontrollers in like the FRC like games for all kinds of things. So it's good to get your start there for sure. Yeah,
for context, we used a Jetson TX1 as a code processor for our vision. And we basically communicated with the RoboRio using UDP networking. So you can definitely use that stuff later on.
Yeah.